Yep, great. Okay, so let's not good. So let's continue. Okay, so as I told, today we are going to discuss some blackouts, some interesting investigation. First of all, about the very famous in Europe blackout in Italy in year 2003. Yes, some analysis about the protection and automation operation, and we need to deal with some tasks. That's why we need some formulas and some tasks, yes, to see. Okay. So let's start with maybe let's start with a map. First of all, I want to show you one new organization. It is for Europe. It is INSTO-E. So this is the European network of transmission system operators of electricity, represents 43 electricity transmission system operator, so TSOs from 36 countries across Europe. And okay, go here. I have opened from their homepage a map of Europe. It is okay. We need to put it here. It's a PDF file, just a huge map with almost all transmission lines and interconnections. Very interesting. So we could see where we are, for example. Okay, let's go to the Baltic Sea, Baltic countries. We could see what is going on here. Maybe some legend. Okay, what we could see here. So we could see not only transmission lines. Here see the voltage of transmission lines, the standard voltage, yes, DC lines, and power plants. So yes, about this power plant portfolio, what is this is biogas, biomass, fossil fuel, gas, oil, nuclear as well, and if I'm right, here is a special mark for planet. So what is in operation and what is in construction. So but no other plans. Okay, this is another version of like this map, because there must be one more. So okay, no, it is okay, but I will. So if it is this left side label, it is in operation. If it is right side label, it means that it's in construction. So that's how it is in this. Okay, so it is about the label. Let's go back to the, for example, for beginning to the Nordic countries, for example, where we are. Well, first of all, you could see what is the difference. What is the difference in topology, in transmission line topology, for example, for the Central Europe and for example, for the Baltic countries. You see the difference. But we need to remember that, as I told you, that, for example, Baltic countries and this Baltic countries power system is very, very reliable. But the population is very low. That's why the voltage, first of all, the level of voltage here, could see that the voltage, okay, come back to the legend, red lines to show you. You see the red line 500 kVs, yes, so higher voltage, because in Baltics we have only 220 and 330 kVs. Yes, so we don't need so high level of voltage to transmit enough power because population. Yes, three countries, for example, Baltic countries is only about 5 million people. Yes, so if we see what is going on in Sweden and Finland, yes, the population or Norway, the population is slow, but the distance, you see, the distance is huge, and that is the reason why do they need more high voltage, because you understand, distance means we have losses. Losses means we have expenses. Not good. And if we raise voltage, we could push more power, but we decrease losses as well. That is the reason. High voltage is good because we decrease losses in our system. That is very important. So if you could afford more high voltage, it is good in two cases. But if even you don't need to transfer so much power, high voltage is good because you have less losses. Okay, this is about the topology, about the generation. You could study this map, it is very interesting, but one, because a key point, it is for Europe, because InstaE, it's European organization for power system operators, not TCO, because TCO plays a role of power system operator. Okay, let's go to the south of Europe, Mediterranean Sea. Here we see the Italy. Why do we need map? We need to understand the geography and the transmission line topology, first of all. Okay, this is the Italy, and Italy is geographically connected to the Central Europe through, okay, let's increase some delays because map is this picture, no, this is PDF, it's typical picture is huge. That's why it takes some time to decrease. Okay, here we could see countries as well. Okay, maybe a little bit. Yes, this is the border line. Yes, for Italy. Here you could see. Yes, Italy. And Italy is connected. No, geographically, border to be true, right word. So this is France, Switzerland, Austria, and Slovenia. So, and here we could see interconnection lines. Yes. So we don't see high voltage with Austria. So we see several lines with Slovenia. Here you see this goes to France. And these lines, we could count the number of lines. I'd say with the highest voltage, the number is only 3. Yes, go to Switzerland. So this is how Italy is connected to Central Europe. And one more very important key point is about the Italy energy balance, about the generation and consumption. So Italy power system is a deficit system. They generate less than consume. That's why they need to import electricity from neighbor countries. Okay, so there are a huge number of reports and hundreds of pages. That's why, if you wish, you could download any in internet and go through all these reports, but I'll use my students' master work. Unfortunately, it's in Latvian, but we need only some keywords because I explain it very short. We need some keywords, some timetable about this how to say, how it was in history, and then some data. That's why I think it will not be a problem. Okay, where it is, master work. Okay, yes. Okay, mouse problem still. Okay. Okay, so this is okay. The small map, yep, about this connection. So here we could see, okay, I can maybe, okay, decrease, can zoom in. So, okay, Italy, neighbor countries, and here we see interconnections. So, red lines we could see here in a table, not here, maybe, okay, there is a once more one comment. So there was a table where it is a table. No, it is the end of the story. We need the very beginning of this story. Okay, yes. Here we could see two types of voltage. So 380 kVs and 220 kVs. So red line 380, green line 220 kVs. And there is the number of lines. So France 3, Switzerland 3, Slovenia 1. And number of 220. 1 France, Swiss 6, Austria 1, Slovenia 1. And there is one more DC cable to the Greece. Yes, so okay, let's open the map, because Greece is a little bit here, and you could see this cable, yes, underwater cable about this DC. So in the south of Italy, yes, connection to the Greece. Okay, but what is more interesting, let's go here to the map. So yes, these lines. So mainly Switzerland, yes, we see two lines here. Is it, if I'm, it is, yes, two lines. Two lines 380 and others 220. Okay. So interconnection. About the balance. Next question. What was the balance before this blackout? And here is a table again about this balance, where it is. Okay, this is a table. So this is the load, total load. This is a mistake. This is giga. Okay, the total load was about 27 gigawatt of power. But the Italy production was about 20. Yes, here we could see this is the number of import in megawatts. Yes, so okay, let's round this value 7 gigawatts. So import was 7, so it means that internal generation in Italy was 20 and 7 was from neighbor countries. So 7 to 27, okay, let's just percentage. 7 to 27, it's about 20, okay, let's round 25%. 25% is import. So quite a lot. Okay, quite a lot. So it was in a deficit. Let's go through the timetable of this. Okay, at 3 a.m., so at night. Oh, once more important value, the temperature, line temperature. And this is a physics. And this is quite typical problem for transmission lines, because I just want to highlight this moment. I need not so much. Okay. Just want to draw an example for you, because this is quite important. This is quite typical problem, and it is important. Okay. So transmission lines goes. This is a physics. So there is a current. Yes, current flows. Oh, so I need a pen again. So current. If current flows, it means that there is a heat effect. Current, no, in other words, power heats the wire. The more power we transmit, the higher temperature is in the wire. So, and at the beginning, the temperature was about 80 degrees, so Celsius, quite hot. And what is going on with a wire when it heats? So this is a physics, because wire, it's a piece of metal. And what do we get when the wire heats? Yes? What is going with wires? What is going on with wire length when, okay, you just draw a wire with a higher temperature. What's going on with wire? More high temperature, the length of wire decreases more. And in some time, when the length is quite big, different phases could touch one another, or wires because can touch trees or anything else. And as a result, there is a fault. Is it clear for you? I hope so. So it means that if we overload wires, we have problems with wire length and possibility that phases could touch one another or touch any other object around. That is why there is in any datasheet for wires, for cables, yes, about this temperature limitation, about this possible length increase, and so on. And there is, let's open back, this, and here is this story that in this time moment and 3 a.m., one of two 380 kVs power lines connected Swiss and Italy was loaded to 86%. So this is not, how to say, criminal. This is no so high, but you see there is connection. It is geography. Where is Swiss and where is Italy? Mountains, Alps, a lot of trees, mountains, so on. So very high probability that these, how to say, wires could touch something. And this was the reason, due to the increase of the length, the wire touches the tree, and as a result, fault. We have a current protection. Current protection disconnects this wire. What is more, there is a special automation. It calls reclosing. Yes, that tries to connect back this wire, because okay, no tree, just touch it, and it is enough. Not enough, but it is okay. So just a small touch, and everything is okay. But automation don't know, is it a problem or not? So we need to react on this touch. So that's why automation disconnects this wire and then tries to connect it back in a hope, with a hope that everything is okay. Automation tried, but this connection to the tree was still and disconnect back. In this case, we need to go to the map. Okay, what we see? So one line is off, but we still need to import 7 gigawatts of energy. That means that other lines that are still in operation must transmit more power. As you know, more power, more current, more heat, and as a result, problems with wires length. And as a result, after some time, the temperature of the second line, high voltage 380, yes, temperature decreased, wire length decreased, and a new touch to the tree. As a result, disconnect one more line, very high voltage line. We have lost 2 lines, but still we need to transmit 7 gigawatts. The same result, all other lines must transmit more power. And as a result, overload for lines. And there is a special protection for the overheating, because it is clear that it is dangerous. In this case, it was when it was the first problem that the load was on 86%. As I said, it's not criminal. Just based geography, trees, mountains, and so on. That's why there was a touch with a tree. But this was high, but not criminal. But now, when we lost these 2 lines, the overload for other lines is criminal, and its own overload protection start to disconnect other lines. That is the chronology. Okay, so 1 minute. In 24 minutes, we lost the second line to the Switzerland and begins. After the 4th second, other lines are overloaded and we start to lose lines to Austria, to Switzerland with lower voltage of 220 kVs and so on. As a result, okay, at time 25 minutes past 3, Italy was totally disconnected from Central Europe. Of course, we need to admit this moment that when we lost some connections, we start to have problems with electromotive force angle. Different power systems, connections, electromotive vectors should follow one another, yes. And when we lose these connections, we started with these problems because one power network has overproduction because it can't push this power, but another power system can't get this power and it is in deficit. That's why overproduction rises the speed of electromotive force rotation as it is a frequency, and another one that don't get this power, frequency drops, the speed of rotation of electromotive force vector rotation decreases. Problems with this angle. As a result, one more protection that follows this angle disconnect other lines as well. And as a result, okay, to recap, 25 minutes and Italy is disconnected, totally disconnected from Central Europe, with a result of almost 7 gigawatts of deficit. I'm very sorry, I have a call. Short. Yeah, students per diplom, my student for master work. Okay, so let's continue. As a result, we have a deficit of 25% as we calculated. And what to do? What to do in this case? First of all, we need to push generation in Italy. But as we understand, of course, it is in deficit. It is impossible to find almost 7 gigawatt of power immediately. There are no power plants that could produce so much power. We just try to, a little bit, increase existing power plant is its power a little bit. We have about 5% of reserve. It is maximum what we could get. If we run all on full power, it's not enough. That's why we are in a situation very, very dangerous. But as you know, we have this special automation. Let's go here because this feature is very interesting. It is time, it is frequency. We have two curves. This is frequency and this is imbalance in time. Okay, here what we got? This disconnection. Point of disconnection. When we have the imbalance, here it is, number of megawatts, and here we got the frequency. So, imbalance in imbalance of 7 gigawatts. As a result, we have an immediate frequency drop. What to do? We need to balance the system. The only way to disconnect the load. And it is described step by step, based on the set point. Start to disconnect the load. And here we could see, this is a BAM balance. You see step by step, start to disconnect the load. Top. Here we go, I think here you see 3 AM, 25 minutes. Here you see 25 minutes, 30 seconds. And imbalance is 0 in 26 minutes past 3. So it took 30 seconds to restore the balance, to keep the system back to balance. So, very good. But what we see with frequency, a frequency dropped to the value of 48, I'd say 0.3 hertz. And as I said last time, the frequency below 48, also of course it depends on the power system, its size, inertia, and so on, but somewhere from in range of 47 to 48 is the blackout. So we are here very close to the blackout, to the death of power system. Yes, it is in balance, very, very good, but frequency is low. And here is a table, very interesting table, that describes what I said last time, that if we have the low frequency, we lose power generators. And here is the list, the number of aggregates, no, of generators with its power that we lost when we lost after the system is rebalancing. No, when the system come back to the balance. Due to the low frequency, we lose all these generators. You see, this is a total power. Okay, this is 31 generators with total power of almost 6 gigawatt was lost due to its own protection. No, because the frequency was too low. I showed you that every generator is very expensive. It has its own protection. If it is low voltage, if it is low frequency, and so on and so on. What is more, for example, this is okay, this is clear, this is its own protection. But there are some other very interesting reasons for other generation that have lost. For example, there are many issues, but very interesting just to you have this how to say overview about what's going on. For example, steam turbine, CHPP. You have steam flows. You have different pumps for system operation, this cooling, heating, and so on, so on, so on. And as we discussed it last time as well, that if we have the low frequency, it means that the pump gets lower power. As a result, this pump for power station operation can't do its function. As a result, problems in this technological process that pumps can't deal with its function. As a result, another problems in some nodes of the system. As a result, disconnection again. So, for example, oil. This is cool, not cooling. Oil overheat. A lot of different reasons could be, but as a result, so motors, pumps, and so on that make this power plant operation can't do their function. They do, but can't, how to say, produce enough or cooling or enough oil, yes, for and so on and so on and so on. As a result, we lost huge number of power generators due to low frequency. Okay, what to do? We lose generation power. That's why we need to disconnect more load to restore this balance as well. And here we could see, here we start to lose generators, power losses. When you see this is surges, yes, that's of balance. Okay, imbalance, come back, disconnect load, come back, disconnect load, disconnect load, disconnect load, and so on, until we disconnect all possible load connected to this automation. No, and as a result, frequency lower, more generators lose, and the result here you see the frequency drop to the 47 hertz and total blackout. We lose everything. This is the result. What analysis could be done for this? First of all, as I mentioned last time, maybe I need to open this is, I think, maybe this one. There we go. Very nice. Yes, this one, very nice picture. So in this case, what we see when we have this point, when we come back to the balance, we need in this point, yes, to disconnect more load and to increase the frequency as this do this AAF2. So as I said that in Western Europe there is no automation that restores this increase the frequency due to this fault situation. And there is a result. So the task to increase this frequency, to restore the frequency, is a dispatcher center task. So system operator manually must do this. But you see, the dispatcher, system operator don't have enough time to do this manually, to call to power plants, to plan, do this. Don't have enough time. That's why if they had one more automation, yes, there's one more protection, and they restored the frequency, everything was good. But unfortunately, it goes to all of this goes to blackout. And one more very important conclusion about the situation. You see that the only one interconnection loss, so lose one line, lead to the all other lines overload. As a result, dangerous situation. I think this is the problem number 2, because there is a very well-known criteria. It calls N-1 for power system design and operation. What does it mean, N-1 criteria? It means that when you design and when you plan the operation mode for power system, these criteria N-1 should be true. What does it mean, N-1? This is a number of elements in power system. And N-1 means that loss of any one element of power system. So it means that if you lose any element of power system, any line, any power generator, any substation, your power system will continue to all its functions without any problem. So in this case, they lose one line, and as a result, overload of our line. So this means that N-1 is not true. So this is a fault of system operator, because this operation mode is incorrect. This is the second problem. Yes, there are a lot of interesting papers, scientific papers, discussions about this N-1 criteria. Some very also smart guys said that this criteria is not good, and so on and so on. But unfortunately, okay, maybe this criteria is not good, but still, if this criteria N-1 is not true, very often we see critical situation, and as a result, the blackout. That's why, from my point of view, when we don't have anything better, we need to follow this N-1 criteria. So once more, when you design your system, this is when you build a power system. And then when you plan the operation of power system, because there are a lot of things you need to, some maintenance, you need to disconnect some lines, transformers, substations, and so on. And the power system operator says, okay, could you disconnect this element or not? So operator gives this permission to do something because operator plans the configuration of power systems, is topology, to be sure that everything works okay. That's why it is fault of this mode planning, because the operation mode was not good. N-1 was not true. The loss of one line, as a result, over all other lines are overloaded, and you are in danger. Because when lines are overloaded, it's only a time question, then its automation, its protection will disconnect these lines. So so the condition when all of we have overload lines means that we have the starting time when we need to do any operations to save power system. See, there was 24 minutes from the beginning of this scenario. So disconnection, it was 1 minute past 3, and we lost the second line 25 past 3. So there was 24 minutes to save, because it was known that, mouse problem, all that our lines are overloaded. Yes, you see, overload was 110%. No, its load was 110%. So overload. Yes, so the second line disconnected from the protection because it touched the tree. But if there was no tree, the result was the same, because its own overheat protection will, or not will, but it is in the past, disconnected this line, maybe a little bit later. So, but for these 24 meters, 24 minutes, the system operator could do nothing. Okay, this was the case. Maybe you have some questions about this Italian blackout. Okay, if you don't have, we could go to our tasks where it is. Okay, maybe this, I can use this. I need formulas. Maybe another document. I will open another document with, okay, no, it's good enough. Okay, so there are some formulas for your underfrequency protection design. How to calculate set points. And what do we have here? First of all, formula 4.5. This formula helps us to understand what could be the minimal frequency in a system if we have such load connected to the under frequency automation. So this is AAF, this is in Latvian. Yes, this is our automation, under frequency automation, and the power connected to this automation. So what do we have? This is, so we calculate this minimal frequency system, in case if we disconnect all this load connected to this automation. So this is nominal frequency, because this formula true for any system. If you have 60 Hz, if you have 50 Hz, just put in formula the right number. This 1 minus 1 divided by Kn, this is load reaction coefficient. This is formula, but typically this value is known. And as I showed you, that the name of this value could be the big D letter, and it is in percent. So maybe once more time, what is this load reaction value? It shows that what is difference in power for the load when we have a frequency deviation of 1 hertz, and it is in a percent. How much? Yes. This is PG. This is all generator power. This is PSL. This is the load power. And this is a load power connected to the automation. So in this case, we could calculate this, what is the minimum frequency could be. So we have, sorry. This is delta. This means that this is not, this is power, generated power, but how much power we lost. This is delta, difference, how much power we lost. So yes, this is the total load, this is how much power we lost, and this is how much power could we disconnect. And this is the answer, what will be the frequency. Based on this formula, we could calculate how much power do we need, how much load power do we need to connect to the automation if we want that frequency will not be below this F mean value. So how much power must be connected to this load power, to this automation, not to allow that frequency will be lower than this value. And what is more, if we have two types of automation, this is that keeps the balance, and this is that restores the frequency. We could say how much power must be, for example, connected to this automation. So this is to part 1, this is part 2, that restores the frequency. How much power, load power, do we need to connect to this automation to restore this is a FATJ. This is a, how to say, restoration, the power we need to restore the value. And typically, for your understanding, this is this is first part is about 40-50% of all load is connected, and to the second part about 12-20% if we have the second part. And what is more interesting, before we try something to calculate, is some I think not this one. Some interesting information about how this automation is used in different countries and how this load power is disconnected through this frequency set points. For example, this is a Portuguese. Yes, this is a Portuguese. The first stage is at 48.5 hertz, and at this stage, all this how they call it in English, this is hydro pump power plant, when you could pump up the water in a, how to say, in a pump mode, you can pump this water up, and another time you could convert this water to an electricity. So if you have this hydro pump power station in pump mode, then you disconnect this. For the first stage, you disconnect this pump mode. When the frequency drops to 48 degrees, you disconnect 15.6% of the load power without any delay. After 150 milliseconds, you disconnect 80% more, and in 500 milliseconds, 0.7% more. Why? Why very strange set points? No, this is, of course, I can't explain in details, but my suggestion is that is based on their experience about what problems could appear. That's why they calculated this amount of power to disconnect more, because precise, more accurate, the enough power. So 2 stages, and this is for the small, regulation. So this is next, and so on. So the most load power we disconnect at the beginning, and then we try with small amount, yes, to find this balance. This is in Portuguese. What else interesting? This is Israel. Very interesting as well. You could see this is, okay, this is in value, megawatts, and this is in percent. So the same idea, a lot in the beginning and then a little bit. But okay, here is a big stage again. No, so in different countries, they have different experience and different stages is in, like it is in frequency set points and this load power connected to every stage. Okay, so we need at least one task. Try to calculate. We could vary. This could be okay. I think it is yes. Okay, so let's try. This could be deleted, and okay, what we have. So we have a frequency of 50 Hertz. System 50 Hertz. We have P load 1000 megawatt. What else we have? We have this D, this load reaction. I think 1.2, and I said its maximum value is about 3. So it could be a big value. Next, delta PG, power we lose or deficit, it is 300. 300 megawatts. 300 megawatts. Okay, and we have this and we have 200 megawatts connection to this auto frequency automation. And we need to say how the frequency will drop. Okay. So this is what you know, and formula for you. Okay, where it is. And here is a formula for you. So please try to calculate what will be the minimum frequency.